Right, so welcome to the second lecture. Today we're going to be talking about flexure design. How do you design a beam in flexure? For those who were asking. So let's start with this interesting example. Let's say you are hired by a developer of a tall building to design a structure like this. How would you do it? How would you structurally design a building like this? Where would you start? What would you do first? Hire an engineer? Well, they hired you. They hired you to do the work. So you need to start thinking about the design process. Let's think about this. What would you do first to design a building like this? Yeah, go ahead.
Take the master plan architecture layout and then transfer them into a structured one and then start building from the foundation and calculating the moment and the beam section, how big.
I love it. That's exactly it. That's exactly it. Any other thoughts? Anyone heard this answer? What would you do first to design a building like this? Start with the architecture plan. See how the architect wants the building to look like. This is something that architects help us figure out. The second step, figure out the floor layout. Where you're going to put the columns, the beams, to create this structure. So, in other words, if you want to build something like this, first you need to think of the structural elements. What are the structural elements that you can use to build a high-rise building? Can you think of structural elements that you can use? I'm going to need a volunteer to move on. Structural elements are very basic for structural engineers. Thank you. Beams, columns, slabs, perfect. Shear walls, cross bracing, these are all structural elements. Each element of those you need to design. You need to design, you need to choose. So what do I mean by design? How do you design a structural element?
Choose the section if it is already pre-manufactured,
Yeah.
or design the built-up sections for the all elements of the building.
Yes, you're on the right track. Any other thoughts? How do you design a structural element? Let's say a beam. A beam is a structural element. How do you design a beam?
Figure the load.
Calculate forces and moments.
Calculate forces and moments on the beam.
First, identify what material you want to use.
Choose the material, that's part of the design. So these are all part of the design process. You choose the material, that's part of the design. Calculate the loads, part of the design. Any other thoughts?
If you're going with a manufacturer and you want them to produce it for you if they're already pre-produced, like they come and review, you have to see the table sections, what they offer, and then see the closest one according to the moment of inertia, according
Yes.
to the loads, the weight.
Yes, I love it. So how are these tables calculated? Do you know how these tables are calculated? Which tables are you referring to? The dimensions or the how strong the section is? Both.
Both.
Both. Okay. So how do you figure out the strength of the material or the capacity of the section? How strong the section can support the weight or the load on it? Testing. That's a very good thought. You can start with testing. So I'm hearing very good answers. I just want to make sure we're all on the same page. What I asked about, how do you design a steel beam? And I've heard something like, calculate the load on the beam. Yes, that's step number one. So where does the load on the beam come from?
The live load that supposedly should be on the beam or the structure.
Absolutely. So you think of, okay, the building is going to look like this. It's made out of structural elements. First, figure out the load. The load comes from the weight of the people, the self-weight of the structure, wind load, seismic load, earthquakes, and all these types of loading. All right. How do you figure out the magnitude? How much is the life load on a building? Any other thoughts? How do we figure out the live load on a building? I need you to think about this one.
Use of the building. How it's going to be used, is it residential, commercial?
Yes, yes. It depends on the use of the building, and then you reference to the local codes, and it will tell you how much weight of users of the building you should use. Perfect. So once you get the load on the building, what do we do next? Now you know the load, you calculate the bending moment and shear force and reactions. What do you do next? Is that you're done with the design, you figure out the load, and you design the beam?
Calculate the shears and bending moment.
Calculate shear and bending moment. Perfect.
Then using the unfactored load, we use figure the deflection.
So, yes, you're absolutely right.
The area of the elements of the section.
I just need, yes, you're absolutely right. I just need you to answer this question to move on. Once you figure out the bending moment and shear on the beam, what do you do next? Choose your section. So this is the design. The design is to choose the section. When you choose the section and choose the dimension of the section and the material, you've designed it. Yes, go ahead. You can do it after the lecture. So, how do you choose the beam? What beam is good enough to support the weight of this floor?
The moment and the inertia and everything you've calculated, you see which one applies in your section.
Yes.
In the tables, and then you see what's the best option to withstand all so that it can, for example, if you have a moment of 82 and you have one that's 80 and one that's 83, you're not going to take the 80, you're going to take the 83.
That's exactly it. So you design the beam by choosing a beam that is strong enough to take the forces on you. That's how you choose it. All right? So now I ask the question, where do you get the loads? The loads come from the weight of the people, the wind load, seismic, and those are referenced in the code. How do you get the strength of the beam? How strong the beam is? What's that? From the code as well. And I've heard experimental, like you can test it. You can test the beam and you see how strong it is. But the design codes give us formulas that we can use to calculate how strong is the beam. So think of two numbers. Load on the beam, how strong the beam is. Which one you want to be bigger than the other? You want the load to be bigger than the capacity of the beam, or you want the beam to be stronger than the loads on it? There you go. And that's the most important objective for design. You make sure that the resistance of the section is bigger than the applied load on it. So what we're going to be doing throughout the term is always figuring out two things. How much is the load on the beam, and how much is the capacity of the beam, and make sure that the capacity is bigger. So what do I mean by factored load and factored capacity or factored resistance? Let's start with the load. What is a factored load? Yeah?
It's the load that's actually applied on the device, and the factored resistance is how much load the beam can withstand, or your structural component can withstand.
So you're on the right track. What I want to say is factored load is the actual load multiplied by a factor of safety. So the factored load is the actual load multiplied by a factor of safety. So these are the load combinations that we combine dead load and live load according to the code. Factored resistance is what the code tells us the capacity is, taking a factor of safety in the material strength. So we will see that in example. This is the structural design process. For any structure, for any member, you need to go through this chart. There are two main checks or two main designs that you need to do. The ultimate limit state design or check and the service limit state designed for check. What's the difference between the ultimate limit state and service limited
This
state?
is the multiplied by factor, and this is
Any other thoughts? I see a lot of heads.
Serviceability والتاني safety.
Yes, okay. Ultimate limited state has to do with the failure and safety of the structure. It's very important. Service limited state has to do with the comfort of the users. There are two main checks in service limited state design, and there are four main straining actions or collapse mechanisms or failure stresses that we need to check for. For service limit state, we use unfactored load. We use the actual dead load and live load. For ultimate limit state, we use factored load, like the 1.4 dead or 1.35 dead plus 1.6 or 1.5 live, these load combinations. All right, so what are we checking for serviceability?
deflection.
We check the deflection. We make sure that the ceiling is not going to deflect too much to break the ceiling tiles. There are two types of deflection. There is vertical deflection, that the beam is not going to deflect vertically, and horizontal deflection as well. Like under wind, if it's windy outside, the building is not going to move sideways.
Is it like buckling?
Buckling is under axial load. The element itself might buckle. This is different. This is a horizontal force acting on the structure. Can you think of a horizontal force acting on a structure? Earthquakes, perfect. Any other loads that can act horizontally? Wind, absolutely. Those are the main ones. There are other ones. We can take an example. Can you think of an example other than wind and earthquake that could cause a force, horizontal force on a structure and cause it to deform or deflect sideways? Waves.
Like bombing.
Blast
Yes.
load, that could be,
Like
yes.
something-
Yeah, that's actually an example. Blast load. If your building is sensitive to vibration, you might want to design it for something like that. There are things more common though.
Water waves.
Waves that would work. So what would be the structure applied? Dams, bridges. Okay, that was the example I was gonna go to. Do you have a thought?
I said natural disaster.
Natural disaster would put like a horizontal force, like earthquake.
For example, tornadoes, tsunamis.
Okay. There is a very common force on bridges when big heavy vehicles slam the brake. All that friction will be transferred to the bridge as a horizontal force, so braking force. That could be an example. Also in industrial buildings that have cranes. I'm gonna show you like how that works. When the crane stops, it puts like horizontal force on the structure. These are the service limit state checks, and we check them with unfactored load. That's very important. For ultimate limit state, we will check the capacity for the section that is strong enough to withstand the forces on it. So what are the forces that can be applied on a section?
Loads.
So what is the main force in this structural element? What is this structural element?
Column.
Yes, this is a column. What is the main force on a column? Tension or compression. It's called axial load. You're absolutely right. So on a beam, what are the main forces on a beam?
Slab. Shear. Load. Load of the slab.
Yes. What are these loads going to create on the beam? They're going to create shear and bending. That's right. That's what I'm talking about. So you look at the element that you're trying to design and figure out the internal forces. Is it axial load? You design for compression or tension. Is it bending or shear? You design for bending and shear. Which leave us, so you design it for shear. This is the effect of a shear on a beam. It's trying to shear it off, like scissors. Scissors apply shear force on like a bar or something like that. Bending is like the flexure. It will cause compression on one side and tension on the opposite side. This is compression and tension. I want you guys to be aware of this type of load. What is torsion?
Rotation.
Torsion is rotation about the longitudinal axis of the beam. So what would be exposed to torsion? Where would torsion come from?
ممكن لو
If you're having like a parking structure that has like a canopy that looks like this, and this is a column fixed at the bottom, and the cars would like kind of park here. The weight of this structure, if this was a box beam or like an I-beam, it will cause torsion. Like this moment is causing torsion on this beam. So torsion is you put your finger in the longitudinal axis of the beam. Your fingers are showing you the direction of torsion. So you need to check if there is torsion, you check for it. No torsion, you're designing like a simple beam. Most probably it has zero torsion on it. So you don't have to check.
most has zero torsion.
What's that?
يعني لازم تكون zero torsion أي حاجة.
It
ما
doesn't.
ينفعش يكون في torsion.
Well, if there is a torsion, you design for it. The code gives you the equations to design for torsion. Does that make sense? So, long story short, for each of these actions, the code will give us an equation to calculate the capacity of the section. Today, we're going to focus on bending. We're going to explore the code equation to figure out the capacity of the beam in bending. We're going to spend some time going through equations to eventually figure out how much is the section capacity in kilonewton meter, or like force times distance. What do we do with this number? Why do we need this number? Why do we need the capacity of a section in bending? To compare it to the actual load. So you calculate the load on the beam and make sure that you choose a section that has a capacity that is bigger. Does that make sense?
Yes.
No? I want the resistance to be bigger than the load. The resistance of the section to be bigger than the load. How do you figure out the resistance of the section? From the code equation. So I'm going to go in the code equation and figure out how much is the bending capacity of the section from the code. And now I have the right hand side. So what do I compare this to? To the applied load, to the dead load and live load. Does that make sense?
Okay.
And just make sure that the capacity is always bigger than the applied load. All right. So let's take an example of a simple beam. If we were given the dead load, or you can actually calculate it. You can calculate the finishes, the self-weight of the slab, the self-weight of the beams, and that will give you the distributed load or the uniform load of the dead load. You go to the code according to the function or the use of the structure, you figure out this is residential, and you get the live load. So you have live load and dead load. And you use the load combinations to get factored load. Once you do that, you can plot the shear force and bending moment diagram. All right, so now I know the applied load. I need to design this beam to be strong enough to withstand the factored moment. So how much is the moment on a simple beam with distributed load? W all square over 8. So very quickly, first step, you can calculate the demand. How much moment is applied on the beam? You can get it from dead and live. Now, to design the beam, you need to choose a section that has a bending capacity bigger than the applied load. How do we get the capacity from the code? This is the standard for the European code, for the Eurocode. And by the way, I talked about this. These documents are very important. So you might as well start building your library and get the actual code to look at these equations. These equations are in the code. So section 6 talks about the resistance of a cross section. We want the resistance to be bigger than the actual load. So let's figure out how to calculate the resistance of a cross section. This is the simple equation. The effect, E is for the effect of the load, should be smaller than the capacity of the section. It's the exact equation I did, but as a ratio. So if you divide the demand, or like the actual load, you divide it by the capacity, it should be less than 1. So the capacity should always be bigger. So here's my question. How do you get the moment under the load, the effect of the load from bending and live, from dead and live load? How do you get the capacity of the section? From the code equations. So the code equations tells you how much is the capacity. All right? So if you look closely, there are 3 equations to calculate the moment capacity of the beam. Each equation is dedicated for a class or type of section. So what are the classes of the section? What is like class 1 and class 2 sections?
Dimensions of the sea and
That's what we did last week. We already know how to figure out the class of the section. You look at the yield strength of the steel and the geometry, the width and length, and decide is this class 1, class 2, or class 3. Class 1 is the strongest. If the section you choose, let's say an I section, IPE or a certain type that has certain depth and certain width. Which beam should I use? I need to use a beam strong enough to resist the load on it. So I'm going to be looking for certain dimensions. Choose that section, use that equation, and see how much is the capacity of that section. If it's bigger than the applied bending moment, the section is good. If it's smaller, I need to choose a different section. So if you choose a section way bigger, way stronger than what you need, this is uneconomic design. You're charging your client for way more steel than they need to pay for. So you need to choose the lightest section that works for you. Do you understand what I mean by the lightest section?
yes, that can handle the load, the factored load, and still be cheaper than the.
Exactly. So safe enough to resist the load, and not too big or too heavy for the loads applied on it. This way, you can have a sustainable and an economic design. So let's choose the code equation for class 1 and class 2. It says the section capacity in bending follows this equation. The capacity of the plastic limit of the section means that if there is a bending moment applied about this axis, so what would the bending about this axis look like? You put your finger in the direction of the axis, and you put your thumb in the direction of that axis, and your fingers are showing you the direction of moment. So this will result in a stress distribution. If this is the moment, you're going to have tension stress at the bottom and compression stress at the top. And it goes linear. It goes from tension at the bottom to compression at the top. And these are the values of stresses. So where is the maximum stress? This is the stress distribution. Where is the maximum stress on this section? The middle. This is the maximum? Well, this is the value of the stress. So how much is the stress in the neutral axis? 0. There is no stress. Where is the maximum stress? At the very top and the very bottom. At the very top, there is compression stress. At the very bottom, there is a tensile stress. All right? So what is the maximum stress that we can apply on a steel section? How much, like, think of like steel material. How much stress you can apply on steel? How much? 10 kilonewtons is the maximum stress? What is stress? Yes, what is stress?
ضغط, the pressure.
Say this is stress, and this is strain. What's that? It has to do with the strain. Okay, this curve is very important. Let's say you have a piece of steel. This is a bar of steel. The tension force divided by the area of the cross section, so T divided by A, is the stress on this section. It's force divided by area. The strain is when you apply tension, the length of this bar will get a little bit longer. So the increase in the length divided by the overall length. So the strain is the increase in length divided by the overall length. Does that make sense?
Yes.
The relationship between stress on steel and the elongation or the strain looks like this. It's linear, keeps on going linear until it reaches certain stress, and then it cannot take load anymore. And then it pretty much fails. So how much is that stress? This is a number that the code will define. I will show you the tables that tells you how much is that load. This is called yield stress, or F yield. The yield stress. Does that make sense?
Doesn't it have factors in chapter 0.28.5 and here factors?
Yes, so we cannot use that number because I need to take like a safety factor, not just like use the steel to the actual limit. I need to take a factor of safety. So what I'm trying to say is, if you apply force in increments, like force in increments, the elongation or the strain will go linear up to yield. Once you get to the yield, there will be more deformation without additional load. You cannot, the steel section cannot take more load. And this is translated exactly in the stress curve. This part has stress smaller than the maximum stress at the top. What I want to do is make sure that this does not exceed the yield stress of steel. Okay? There is a section, if the section is class 1, class 1 can achieve yield at the entire tension and compression part of the section. So if this happened to be a class 1 section, like this, class 1 section, I can achieve yield stress all the way to the neutral axis. And I can achieve tensile stress all the way to the yield to the neutral axis. So what these distributions mean is the bending stresses on the section. If the section is strong enough, it's class 1, and the distribution will look like this. It's yield everywhere. If the section is weaker than class 1, then I want to limit the top stress to yield and then have it in the elastic range. I don't want the section to be completely plastic. And you will find that the code says to calculate the moment capacity, I need 3 things. I need the yield strength, F yield. How much is F yield? and it gives us tables to choose from. It will need to tell us the safety factor, because we cannot use the actual number. We need to take a factor of safety into consideration. Because what if it happens that there is like a probability that the yield stress is not the exact number we designed for? So we need to create some factor of safety. That's the second factor. The third factor, this is a value called the section modulus, and it depends on the moment of inertia and the geometry of the section. Like, it basically depends on the geometry of the section, the width, depth, and the thicknesses. There are two values: section modulus for plastic section and section modulus for elastic section. The plastic section is when the yield stress is for the entire cross section. The elastic one is when the yield is achieved only at the maximum stress. So the code will say, go figure out the classification of your section. Class 1 and 2, so this would be class 1 and 2, use a section modulus for plastic stress. The entire section is yielding. Because the section is very strong, this will give you bigger capacity. If you do the section classification, and you can refer to previous lecture and tutorial to know how to do the classification. If the answer for your section classification happened to be 3, you can't use the plastic section modulus. You have to use this distribution. All right. If it's weaker than 3, you have to use a different a different section modulus. So the question is, how do we get these numbers? Like, I'm very interested to know the capacity in bending. So I need to know 3 things. I need to know the yield of steel, I need to know the factor of safety, and the section modulus. How do we do that? The Eurocode, section 6, talks about the ultimate limit state, and it pretty much says the factor of safety in the previous equation has these 3 values. The one we're interested in, if you go back to the equation, is gamma m0. So the code will tell you that this document is for the entire European Union, and each country can specify recommended values for them, and then it will give recommended values. It recommends that gamma m1 equals 1. So gamma m1, we're going to use it as 1. Okay, what else do we need? Did we figure out this factor? How much is this factor? 1. Where did we get the 1 from? From the code. The code told us it's 1. All right, so we need 2 more things. F yield and the section modulus. How do you get the yield stress, the yield strength of the section?
Stress strain curve.
From stress strain curve. Okay, where do we get the stress strain curve?
Stress from the maximum stress strain.
The code gives us the stress strain curve. So this table is from Eurocode. It's table 3.1. It gives us the nominal values for F yield. So here is the standard or steel grade. Steel grade is like when you order the parts for the structure, you will specify what is the steel grade. There are different types of steel. Some types of steel are stronger than others, and we give them names. So this type, we'll call it, according to the European standard, like there are special tests and special requirements to fulfill these steel grades. Let's say we're going to choose, this is one of the most common ones, steel S275. The 275 represents the yield stress if the thickness of the section you choose is less than 40 millimeters. So you need to look, okay, what is the section I'm using? And go to the thickness of the web or the flange. If it's less than 4 centimeters, if it's less than 40 millimeters, then This is the magnitude of F yield, 275. What is the unit of this number?
Newton per meter.
Newton per millimeter squared. It's very important when you use the load, the moment. You can't use moment in kilonewton meter and apply F yield in Newton millimeter squared. Just be consistent in your units. All Newton, all millimeters, or whatever the units you choose, just be consistent. So now, do we know how to get the second factor, F yield? We get it from the code. We get it from the table. All right, and this is the strength strain curve that I just explained here. And this is the actual curve. Past yield, there is a little bit more capacity. But just to be conservative, to be on the conservative side, we will use the yield stress as the ceiling, as the limit. We're not going to exceed it. Otherwise, plastic hinges will form and the structure will deform permanently. Once you exhaust the linear part, any deformation here will permanently remain. Even if you unload the structure, it will remain warped and distorted. So if you remember, we needed 3 variables or 3 factors. The factor of safety, we got it from the code. The yield stress, we got it from the code as well. We need to get the section modulus. Do you remember what I said about section modulus? What are the variables that control the section modulus? Only the geometry of the section. So the depth, width, and thickness. I can get this from the geometry of the section. All right? So can you see where this is going? How do I choose the dimensions of the section? The section modulus depends on the dimension of the section. How do I choose the dimensions of the section? Okay. What is the target for this moment capacity? Perfect, that's exactly it. I need this number to be bigger than or equal to the applied load. Does that make sense?
Yes.
So how do I find the geometry that is strong enough to resist the applied load?
اوكي فعشان نجيب السكشن نفسه. اوكي.
How do you get the section geometry knowing the applied load?
احنا معانا اوريدي فاكتور لود حضرتك بتقول اور ايكوال فده معناه المينيمم اصلا.
Yeah.
المينيمم يعني مينيمم ريكويرمنت فاحنا ممكن نجيب اعلى حاجه صغيره او نخليه هو السكشن.
Yes, you figured out. You equate this equation to the factored moment, to the applied load, to figure out the section geometry that will be strong enough to resist it. That's exactly it. So luckily, you don't have to calculate the moment of inertia for these sections like what we did in structural analysis. In structural analysis, we understood how to calculate I for a given cross section. But because these sections are standard, like steel manufacturing companies, they manufacture sections in standard dimensions. It's like the same way when you go to the hardware store to buy a certain bolt or a screw or something like that. It needs to be standardized. Like it comes in certain length, either this length or deeper or like thicker with specific dimensions. So the manufacturing companies will produce these tables. These are the available sections. So IPE is like a European section for the I shape. These are beams that have this cross section. And these are the properties of these cross sections. So you look at the top here for the section that you're looking for. Let's say I'm thinking about choosing IPE 400. So what are the geometry, the dimensions for IPE 400? The depth of the section is H. What is H?
The length? No.
It's over there, you can see.
To the front.
From the very top to the very bottom. So how much is H for IPE 400? It's 400. That's why it's called IPE 400, because its depth is 400. Do we know the thickness of the flange, TF, for IPE 400?
Yes, it's given.
Where?
In
TF
yes.
for IPE 400 is 13.5 millimeters.
Yes.
So the manufacturer will build them with this dimension. All right, so how do we get the section modulus? The elastic section modulus is the moment of inertia divided by h divided by 2, half h. This is W elastic. This table will do this math for us. This table, since it gives us h and it gives us the moment of inertia. So what is the moment of inertia of this section?
Moment of inertia.
Yes. Moment of inertia is the second moment of area.
Yes.
So it has two values. One about yy and one about
Yes,
zz.
the one with respect to the y-axis and the one with respect to the x-axis.
Yeah, so what does that mean? What is the moment of inertia with respect to y-axis?
The second moment of area, the inertia in the y direction and the inertia in the x direction.
This is very important. You're right.
Yeah.
The moment of inertia about an axis is the resistance of rotation about that axis. All right? So the moment of inertia about y line. So where is the y and where is the z or z? Y is the horizontal, z is the vertical. This is the notation for the Eurocode. Egyptian code might put the horizontal x and the vertical y. So why did they choose the horizontal y and the vertical z? The Eurocode assumes that the longitudinal direction of the beam is x, the cross section vertical is y, and the third perpendicular is z. No, like the vertical is z and the horizontal is y. That's why the horizontal is y and the vertical is z. So x is the longitudinal direction of the actual beam. So moment of inertia about y, you put your thumb in the y direction, your fingers are showing you the resistance of rotation about y. The moment of inertia about z, put your thumb in the z direction, your fingers are showing you the moment resistance about the z direction. All right, so I know the moment of inertia about y, and I know the overall h is, the overall section is h. So from this formula, the section modulus, the elastic section modulus, is like I divided by half h. It will give us the math, it will do the math for us and give us the number in centimeter cube. So again, pay attention. If you're using meters or millimeters, you need to convert that number. So there are two values. That's what I want to say. There is the elastic modulus and the plastic modulus. You go back to the code equation. You use the plastic for class 1 and 2. Use the elastic for class 3. Does that make sense?
Yes.
So let's do a quick example. This line here is the Eurocode, and I will go back in a minute to show you the Egyptian equivalent to these equations. They're very similar. Let's say that I have dead load, live load with these values. What would be the factored moment, maximum moment on the beam?
Sorry?
So that's the dead load, that's the live load.
Level factor.
So what is the maximum factored bending moment on the beam? Yes, you're on the right track, yes.
Divided by the factor 1.35 and 1.5. The dead load and the live load.
First, get the factored load combination. So first, get the factored load combination. This is W, the distributed load. So how much is the maximum moment under this factored load? W L squared divided by 8. Perfect. All right. So now this is the maximum moment under the Eurocode load combinations. So what is the section modulus strong enough to resist that load?
Figure 3.
I'm going to equate that equation to this moment to figure out the section modulus that is strong enough to resist that section. Does that make sense?
Yes. And F yield.
You have F yield, we have the factor of safety. All what I'm looking for is the section modulus. When you choose the section modulus, you go in the tables and see which one of those will have strong enough plastic section modulus to resist the applied load.
Do we know which class is it? The class 1 or
That's a good question. That's a very good question. This is, as a matter of fact, this is your next step. Confirm the section classification assumption. If you assumed it as 1, you go back and make sure the dimension you chose is class 1. Does that make sense?
هو انا ممكن اسال سؤال؟
Yes.
هو احنا قلنا في التيبل هنشوف البلاستيك والالاستيك.
It depends on the class section. If the section is class 1, use the plastic. If section is class 3, use the elastic.
فلازم نجيب السكشن بعد كده لازم نجيب الكلاس بعد كده لازم نشوف السكشن بتاعتها
Yes, yes, you're right.
يعني مش بنأسيوم الكلاس بعد كده نتأكد.
Yeah, assume the
Yeah,
class.
assume it at the
Assume it
beginning.
class 1, use a section modulus for plastic, and just make sure that the section you use is class 1.
Okay.
You just confirm the assumption.
Well, I'm confused between the N effect and the other one. The MU, what's the MU?
Okay, MU is according to the Egyptian code.
Okay.
MED is according to the Eurocode.
Eurocode.
So what are the equivalent equations of the Egyptian code? These are the equivalent equations for the Egyptian code. These are the exact equation from the actual document. In section 1, design for strength, the basic concept is the exact same thing. Applied load should be less than or equal the factored resistance. R, resistance, the Q is the nominal load effect. It's the load effect. It's the same thing. There is a factor of safety for the load. There is a factor of safety for the resistance. The resistance, the load. Does that make sense?
Yes.
So how much is the moment capacity? How much is the moment capacity for a section in bending according to the Egyptian code? It's the F yield multiplied by Z multiplied by this number here, because Fn is multiplied by a factor of safety, 0.85. It's the exact 3 variables. 0.85 is the factor of safety. F yield is F yield. Z is W. Z is the section modulus. So Eurocode will call the section modulus W. Egyptian code will call it Z. So it's just like whatever the text or the document calls it. You understand what needs to be done. So what if you were hired to design a structure according to the American standards? Just get the document and see what they call these values. What do they call the section modulus? They're probably going to call it Z and S. Z is for plastic, S for elastic. Pretty much everyone calls yield strength F yield. Yes. The factor of safety in the Eurocode is gamma.
Yeah, it was gamma 0 and gamma M0 and gamma M1 and
Gamma M0, that's right. In the Egyptian code, it's like phi for bending, phi-b for bending, and it's multiplied by the capacity. In the Eurocode, it's divided by the capacity. So it's bigger than 1 in Eurocode, less than 1 in the Egyptian code. That's pretty much it. All right? So we're almost out of time. It took us a while to get through the plastic moment capacity. But before we move on, I need to explain a very important concept. Some beams, because of how they behave in the structure, they will never achieve the yield capacity of the section. They will fail in a different way.
Fail to achieve the F heat.
They will fail to achieve F yield,
So
even though they're class 1.
isn't it better never to reach the maximum?
No, it's weaker. They will fail before the steel fails.
So they will deform.
They will deform, exactly. So that takes us to laterally unrestrained beams. So if a beam is part of a slab like this, the slab is holding the top of the beam in place. If the beam is just like has nothing attached to it, under bending, it could deform sideways like that. So what is the difference between a beam that can deform sideways and a beam that can stay in place until the steel yields? The difference is it laterally restrained or unrestrained? And I'm going to show you exactly how that works. This is a list. I need you to go through it, how to satisfy the design of a beam. First, you need to check the section classification. Second step, you get the plastic moment capacity. We already got that. That's M plastic. You check for lateral torsion buckling. That's if the beam is going to deflect or buckle sideways or not. Once you are finished with this third check, that's the bending check of the beam. You need to check for shear. There are different failure types for shear. We'll deal with this next week. And you need to check for deflection as well. Towards the very end of the presentation, I have the equations for shear. So what is lateral torsion buckling? Lateral torsion buckling is because the top of the beam under gravity load is under compression. Compression is trying to get the length of the top fiber shorter. It's like to compress it. So if the beam is not braced from the sideways, it will go shorter sideways. It will buckle. Just like a column, it will buckle. If the top of the beam is restrained in place, it will not have this type of failure. So how do you keep a beam from moving sideways?
What 12? With the 12?
To what?
To the column or whatever it's jointed.
So that's the column here.
Yes.
So if you weld it well here, you fix it here, and you fix it there. What about the entire length of the beam?
Make a truss or something.
That's going to be.
So you can brace it to avoid lateral torsion buckling,
Trusses.
but sometimes you cannot brace it. Can you think of an example where you cannot brace the beam sideways? That's a good question. Anyone still interested in the discussion?
There's
وانا
second.
مش قادر افهم بالظبط.
What is lateral torsion buckling? Lateral torsion buckling is beams in bending,
Okay.
if they are not attached to anything, will buckle sideways. Will move laterally. They will not. They will deflect and work and buckle.
ايه الريزن؟
The reason is the top flange is in compression. Compression is trying to kind of push it sideways.
بيحصل له buckling الوقت.
The top flange.
The flange not
The
the
top
back.
flange, yes.
Okay.
The top flange will buckle.
في الكرينز لما يكون في لود زيادة وهي is not attached to the cantilevers ممكن تعمل كده.
Yeah. That's a good example. That's actually a very good example. So here is the difference. This is a beam that has a concrete slab on top of it. And this is a bunch of steel beams with nothing on top of it. All right? So think of this horizontal beam. At the very end, it's connected to the column. At the opposite end, it's connected to the column. In between, there are only 2 points that are restrained laterally at the cross beams. In between here, if you apply a load in the middle, this beam could buckle sideways. So you need to design this beam for lateral torsion buckling. So how do you design a beam for lateral torsion buckling?
Make a joint, two triangles in the middle, and a truss, make it a truss.
Oh, you want to avoid lateral torsion buckling. Okay, the only way to avoid it is to make sure the beam is laterally braced at all the way along the beam. The unsupported length is like the distance between these connections. So you need to get these connections to be short enough so the beam doesn't buckle in lateral torsion buckling. That's very important. The first question you ask yourself when you are designing a beam, is it laterally restrained or unrestrained? How do you laterally restrain a beam? Connect it to the floor. You brace the top flange. The bottom flange under gravity load is under tension. It's not trying to buckle. It's trying to stretch. So it's fine. The top flange is in compression. It wants to buckle. It wants to kind of push sideways. So you brace it to the floor. What if you cannot brace it to the floor like that? You design it for lateral torsion buckling. So how do you design it for lateral torsion buckling?
Move the joint and the supports.
The code tells you the reduced capacity to avoid this mode of failure. So the code will tell us the moment capacity for laterally unrestrained beam and the moment capacity for laterally restrained beam. This is very important type of failure that you need to account for. And I would start there. I would start before designing a beam asking yourself, is this beam laterally restrained or not?
طب ليه ما نحط الشمعة تحت نعمل شمعة عمود رفيع يعني.
Over there?
Yes.
Yeah, well, it depends if you can negotiate with the architecture and the builders. If this addition works, that might be accepted. If not, you will have to design it this way.
Okay.
Besides, I'm not sure if adding a column there would brace the top flange.
طب دكتور مش لو عملنا تراس ممكن تمنع الموضوع ده؟
Yes, that's a good question. You can do a truss in the lateral direction. So it would look something like that. Do you see that truss?
Yes.
That truss here is preventing this point from moving laterally. So you can design it into the only span that needs to be designed for lateral torsion buckling is the distance between the braced points. This number here is very important to figure out. What is the unsupported length, the laterally unrestrained length? If there is no cross bracing like this, it will be the entire span. If there are cross beams, like this one here, if there are cross beams, so the unsupported length is the distance between the lateral points of restraint. All right, so let's see some examples. Is the beam connecting this side, is this beam laterally restrained or unrestrained? This beam is unrestrained?
The column.
Interesting. Okay, so let's think of this beam. Is this beam laterally restrained or unrestrained? What is restraining this beam?
The other beam.
Yes, over here. So it's restrained here. What about along the beam? Is this part restrained laterally or unrestrained?
Depends if it's one restraint.
It is. What do you see? This is a window.
It's a one beam.
So is it laterally? What is preventing this beam from moving sideways?
There is another column the other way.
Yeah, so it's restrained at the beginning, at the end.
Yes.
What about the entire length of the beam? It looks like it's unrestrained. Why did you say that? Why it's laterally unrestrained? Nothing is stopping it. When the wind hits that window, it's gonna move that beam sideways. Nothing is stopping it from moving. So what about this beam in the ceiling? Is this beam laterally restrained or unrestrained?
Restrained.
So what do you mean by restrained?
Can move.
Oh, unrestrained means it's free to move. Restrained is like holding it in place. Unrestrained, nothing is holding it. So is this unrestrained, free to move, or something is holding it in place laterally?
Not something.
What is holding this beam from moving
The
sideways?
other beam, beam and the beam.
This beam is holding this point.
Yes.
And the opposite side is holding the end.
The wind.
What about the entire length of the beam? Unrestrained. This beam, this point could move in this direction.
دي مفتوحة ولا في؟
Yes, that's an opening. Even if there was a window, glass is not gonna hold the load. Glass is just gonna shatter and let the beam deform. All right? So that's very important question to answer. When you're designing a beam, think of what is supporting the top flange from side movement. Most of the beams, if they have a slab on top of them, they're laterally restrained. These are special cases. If you're designing something, always check the architecture plan. Is there a big opening next to it, like this one here? If there is a big opening, you might be designing a beam that has no lateral restraint. This is free to move. If you're designing a beam that looks like this, the steel section is physically connected with shear connectors to the concrete slab. The top flange of the steel cannot leave the slab. They're connected together with these studs. These studs are laterally bracing the steel beam. Does that make sense? All right. So in the lecture, you will find the equations to figure out the capacity of the laterally unrestrained section with the Egyptian code and the Eurocode. Let's take a break and start the tutorial and try to crunch some numbers and get these capacities and see how we can use these values. All right? If you have any questions, come see me. If not, see you after the break.
Like, it's
10.
220.
220.
220. Okay? 220.